it's time for us to do 3 types of problems. You're not learning anything new today. That is, you're not, you're not going to learn a new type of force. You're not going to learn any new techniques. I just have to give you harder problems now and let you see how we attack these harder problems and what sorts of techniques work with these harder problems. It's the lawnmower problem, the press the book against the wall problem, and the helicopter problem. And this will help you on tonight's homework. Here we go. First, the lawnmower problem. I have a lawnmower. A man is behind the lawnmower pushing it. He is pushing along a handle which is at a 30 degree to the lawnmower. He pushes with 200 newtons of force. So this guy's pushing on the lawnmower with 200 newtons of force. The mass of the lawnmower is 20 kilograms. And the coefficient of kinetic friction between the lawnmower and the grass, because you kind of fight your way through that grass with the wheels, the coefficient of kinetic friction is 0.50. And we are going to find his acceleration. Well, I'm not going to insult you by asking you what I should do first. I'm just going to tell you free body diagram. So here comes my free body diagram. What forces are acting on this lawnmower? Well, the weight of the lawnmower down, the normal force of the ground on the lawnmower up. Since the lawnmower is moving to the right and the surfaces in contact are horizontal, that means the kinetic friction force will also be horizontal. And then finally, he is pushing down with a force of 200 newtons. Now, your first thought might be to draw your vector in the same way that it's shown in this picture. You're going, well, he's exerting this force down, so shouldn't I draw my vector here? And that would be okay, but the AP exam wants all the forces emanating from the free body. They don't want any forces entering the free body. I guess it makes it easier to grade, I don't know. So when you draw this downward force, you're going to have the initial point of your force vector be on the free body itself. So that force is going to end up looking like this, 200 newtons at a 30-degree angle. You're exerting a force down on that lawnmower. So there's my free body diagram. You know what comes next, some of the forces in the x direction, some of the forces in the y direction. But you'll notice I've got this weird force at this weird angle. What would you recommend I do before I start doing some of the forces in the x and y directions? Thank you very much. X and Y components. And please note, I put arrowheads on my components. That is, if I'm going to start here and end there by walking, I need to walk to the right and then I need to walk down. So I need my components to be pointing to the right and be pointing down. It's a 30, 60, 90 triangle, so I just happen to know that that's what the components are going to be. Half the hypotenuse and then radical 3 times the short leg. But if you need to use your calculator, that's fine. Great. And now I'm going to define up as positive and to the right as positive. Tell me, which direction should I do first, x or y?
Y.
Why the y?
Find normal force.
Yeah, to find normal force. Remember, you're not going to get friction force without normal force, so you might as well find the normal force first. So let's go for it. Sum of the forces in the x direction equals max. Oops. Gavin said y, I said yes, the y, and then I wrote down x. My bad. Here we go. Force in the y direction equals may. I got normal force pointing up. Remember, on the left side of the equal sign, you just list all your forces. I got normal force pointing up, so he gets to be positive. I've got mg pointing down, so he gets to be negative. Do I have any more forces acting in the vertical direction? Which one? Yeah, the 100, positive or negative? Negative, because it's pointing downward. You see why it's so important to put arrowheads on your components. I know it's pointing downward, so it gets to be negative. And then my acceleration in the y direction, hopefully you get that it's 0 because my lawnmower is not going up to the heavens and my lawnmower is not burrowing down in the center of the earth. So it's a 20 kilogram lawnmower, so just trust me when I say my normal force is 296. Now, do you notice that in this case the normal force is not equal to the weight of the lawnmower? mg, which is 20 kilograms times 9.8 meters per second squared, the weight of this lawnmower is 196 newtons. And yet I got a normal force of 296 newtons. Why is my normal force different from the weight of the lawnmower? Yeah, Chris?
Because you're also adding the additional force you're pushing down.
Thank you. I'm adding the additional force. I'm pushing down, right? Normal force is the force of two objects pressed together. I am pressing that lawnmower into the ground more, you know? And so for that reason, the ground is going to exert more normal force up on it. I'm pressing it into the ground. From this time forward, it is a rare occurrence that your normal force is going to actually equal your weight. More often than not, it's not going to be equal to weight, and you're going to have to do some of the forces, you know, in order to find it. Well, let's go ahead and do some of the forces in the x direction equals max. In the x direction, I got 173 to the right, so that's positive. I got my kinetic friction force to the left, and that's negative. And then I got my mass, which is 20 kilograms, times my acceleration. My kinetic friction force is given by the formula mu sub k F sub n. And mu sub k is what, 0.50? And my normal force is 296. Right? And then 0.5 times 296 is 148. 148 from 173 is 25. 25 over 20 is 5 over 4, which is 1.25. And I get 1.25 meters per second squared equals my acceleration. You guys okay with that? Any questions or issues before I give you one to do? Okay, then here's your problem. Same scenario, same lawnmower, same dude exerting 200 newtons of force, but now he is pulling the lawnmower. He's not pushing it. So if I can make a drawing of what's going on, okay, here's my lawnmower. Here's the handle. Here's my 30-degree angle. Here's my dude, okay? But he is pulling on the lawnmower. He is walking to the right, pulling on the lawnmower, which means instead of the force pointing down like this, what's the direction of his 200 newtons going to be? Yeah, up, above the horizontal. So what I'd like you to do is redo the problem, do a different free body diagram, do everything just like this, but I want you to see what his new acceleration ends up being. Good luck. I'm going to walk around and help you. I can't believe the stupid internet died right when I needed it most. Oh, now it's alive. Thank you, stupid internet. Yeah. You know. Yep, same 200 newtons. Everything's perfect. Just you make it so microscopic, it's hard to see what the direction of the components
And
are.
you're pulling it upwards.
Yep.
Okay.
Yeah, get your X and Y components, you got a winner. Free body diagram. Yeah, that's perfect. That's beautiful. That's it. And now your 200 Newton force, you know, is at a 30-degree angle, so that's not a force. So get rid of that horizontal line on the way. Yeah. What's your horizontal or your? Yeah, beautiful. Now you've got a correct free body diagram. Everything you got so far is good. Yeah, good for you. Fatima, don't ever change. Good for you. Brianna. Good for you. But please, put arrowheads on your components. Do you notice that your vertical component is pointing upward, not downward? So you shouldn't get 296 for the normal force again. Oh my God, can I look at your paper? That's like microscopic. How can I even read that? Everything you did is right. Even though it's microscopic. Good. And where's your friction force? Oh yeah. Don't forget that. Imani, so far so good. Well, you just have bad math. You're just horrible at math. I'm so sorry. I feel so bad for you. But this is 196 and that's 100. That's negative 196. That's farther than 100. That's only 96. Yes. Other than math, you did fine. Yeah, beautiful. That's perfect. Let me see if I can get there from here. Oh, good for you. Except your 200 Newton. Where's your 200 Newton force that he's exerting? You need to show me the force vector. On the AP exam, they're going to ask for free body diagram, and you would not get credit for that. Like this force and the normal force are correct, but the 200 should be going off at a 30-degree angle, or they will not give you credit. Yeah, good for you.
Forget this one.
Actually, this is a correct drawing.
No, I don't.
It's just you have the guy walking left instead of right, but other than that, it's perfect.
The books, there's
Oh, okay, so you're not done with the problem.
No,
Everything's
because
so good so far, now
you're
just extra.
pulling it, so
Yeah,
that means
that's
it's
correct, that's the normal.
So
It's 96. It's gonna be positive.
Really?
So here, are you okay with
like
your
that one, you're,
should be
you're
pointing upward?
pushing
That
it
should be a
forward, so that
positive.
means your frictional
So
force
put
would
an
be
arrow on
going
your
the
component,
opposite
it's
direction.
incredibly important that arrow.
Pulling this one, then that means your frictional force should be going to the right.
Ooh, multicolored, beautiful. That's gonna be positive 96, just because when you put a negative on the other side, the sign it becomes positive. Glad I could help.
The lawnmower is going to
No, I'm looking at free body diagram,
Yeah, well, the lawnmower is going this way. The
No.
lawnmower is still going down.
but you still
Free
pulling
body diagram's great. Hey, if the free body diagram,
Pushing
your chances of getting a right answer are very high.
Pulling it, you're going towards the left. If you're pushing it, you're going towards the right. That means your frictional force
Pushing
should
it,
be
you're
going.
going to the right. Pulling it, you're pushing it. You're pulling it to the right.
Yeah,
No,
beautiful.
now I'm confused. That's-
Both ways you're going to the right. Whether you're pushing up or you're still going to the right.
Perfect. See what you got, position right there. Yeah,
So,
everything's going
if
perfect.
we're pushing and pulling, I'm still
You're
pulling.
going to the right, and this is the area.
That thing would fly.
Whatever you use. Do you kissing?
Okay. I walked around and everyone had a proper free body diagram. If you've got a good free body diagram, your chances of getting the question correct are very high. Let's do some of the forces in the y direction equals MAY. Normal force minus mg, and now you'll notice I'm adding the 100, and I just want to say that's why it's so essential that your components have arrowheads on them. It's essential that you know that your y component of this vector is up instead of down, because that changed everything. that made it so that your normal force, instead of being 296, your normal force ends up just being 96, you know? Any question or problem on the sum of the forces in the y direction? Okay, then let's do sum of the forces in the x direction. In the x direction, I've still got 173 to the left. I've got my kinetic friction to the right. I got my 20 kilogram lawnmower times A. And now I'm going to do the coefficient of kinetic friction times normal force equals 20A. And so you get A equaling 6.25. How many people eventually ended up with 6.25 as the answer? Okay, good, good. Virtually the entire class. Can I ask you this question? Why? Why are you going so much faster with this configuration versus that? You're exerting the same force. Why are you going faster? Yeah, Gavin.
Less force is going in the down direction, so you
Normal force.
thank you. There'll be less friction.
Okay, is that what you're going to say, Cole?
Yes.
Yeah, good for you. Yeah, less friction because you have less normal force. Great. If you look at a bunch of lawn care specialists, next time in your neighborhood, actually look for people who do this for a living, who have to mow 10 lawns a day, okay? Look to see how they do it. If they have a normal lawnmower that isn't self-propelling, because I guess there are lawnmowers now where you can press a button and it actually propels itself. But if you have a lawnmower that's not self-propelling, more often than not, your professional lawn care guy is pulling the lawnmower rather than pushing. And the reason, because he knows his physics. He knows it's easier to pull it than to push it. Let me give you another situation. Sumo wrestling. How many people have ever seen a sumo wrestling? Okay, well, sumo wrestling, you get two guys in a ring and they run at each other, and their goal is, the way you win is, number one, push the guy out of the ring, or number two, make him fall down. Those are the two ways you can win. So the two guys run at each other, right? And then they grab each other. They grab each other by a diaper. I used to know what it's called, but I forget what the diaper it's called now. But they grab each other by the diaper, and then this guy's trying to lift this guy, and this guy's trying to lift this guy as they try to power each other out of the ring. Tell me, why should this guy try to lift this guy? What benefit am I going to get from lifting my opponent if I'm going to drive them out of the ring?
Less friction.
Yeah, say again, Imani?
Less friction.
Sure, less friction between his feet and the floor, correct? And in fact, if you're lifting him up, so he's got less friction, less normal force, and thus less friction, what's happening to you?
You have more.
Yeah, you got more, right? Now I'm supporting this dude's weight, so the normal force on my feet is now higher, and the normal force on his feet is lower, and then I can drive him out of the ring. And it's all technique. Since you're both trying to do the same thing, you know, who wins depends on who's better at lifting the other guy up without himself getting lifted. You see what I mean? And I actually watched the sumo wrestlers visit a football training camp where they were together, and then the football player and the sumo wrestler went down, and they were going to go at each other like sumo. So they went at each other. But you got a football player who's taught never to use his hands because that's called holding, versus a sumo wrestler who has to use his hands to lift his opponent. So they went bang, and then the sumo wrestler just drove the football player 10 yards downfield. And the reason he drove him is because the sumo wrestler knew to lift him up, and then he drove him. So the football player's feet are going, ah, and the sumo wrestler's going shh, like that. It looked really cool. Sumo versus football. Sumo kicked butt on football. And that's why sumo's a better sport than football. Okay, any questions or problems on the lawnmower problem? Okay, there's two more types of problems I want you to see. The book against the wall problem and then the helicopter problem. And these are both just me kind of doing them for you so you get a heads up so you can do them on your homework correctly. I'm going to push this book against this whiteboard and keep the book up. The book is up. The weight of the book is forcing it down. what force is countering the weight of the book? That's what's keeping this book up. Is it normal force or friction? How many people say normal force is keeping the book up? How many people say friction? Yeah, good for you. It is friction. Friction is exerting an upward force. Normal force is going that way, so normal force isn't going to keep this book up. But the problem is if I don't exert enough normal force, then the book slides down the wall, correct? And so let's go ahead and do a problem that has that happening in it. Here's my wall. Here's my book. Here's a second. How do you spell physics? Okay, there's my book. Here's my hand. Okay. All right, so this guy is pressing the book against the wall. The mass of the book is 1.0 kilograms. Alrighty, and the coefficient of static friction is going to be 0.60. And to make this an easier problem, because actually the coefficient of friction between the book and the whiteboard is much smaller than the coefficient of friction between the book and my hand. But I'm going to say that the coefficient of friction is 0.60 for book and wall and book and hand. So the same coefficient of static friction. And the question is, find the minimum normal force required to keep the book up. Find the minimum force that my hand has to exert on the book in order to keep the book up. This is a problem where doing a good free body diagram will just save you. Here's the book. Remember, we're doing a free body diagram of the book. Someone tell me, what's one force on this book? What's that?
It's weight.
Sure, it's weight. Tell me another force on this book. Good. What do we call that force? The force my hand is exerting. Which force that my hand is exerting on the book do you want? What's that?
Static friction.
Okay, static friction. Imani says static friction between the book and my hand. Tell me, what direction is that force acting?
Upward.
Say again, Chris?
Upward.
Yeah, upward, right? Static friction between my book and the hand is upward. So we've got static friction between book and hand. Is there another force that my hand is exerting on the book besides static friction? What's that? Sure. What do we call that force when I'm pressing my hand against the book?
Normal force.
Yeah, normal force. So, okay, I've got normal force that my hand is exerting against the book. So that took care of the hand and the book. How about the book and the wall? What's one force that the wall is exerting on the book?
Friction.
Yeah, friction. Good. And which direction is that going? Up. And I'm assuming symmetry. I'm assuming the same coefficient of friction. And what other force is the wall exerting on the book besides friction? I mean, the wall, the book is pressed against the wall. So the wall is pressed against the book.
Normal force.
Yeah, we can say so. Yeah, thank you very much. Normal force. And what's the direction of the normal force that the wall is exerting on the book? Yeah, to the right. And are those two normal forces going to be the same? Yeah, absolutely. Newton's third law. Whatever force I exert on the book exerts back on me. And the book is not moving, which means the wall has to be exerting the same force on the book. And there it is. They're equal and opposite. So let me ask you this. What direction should I be dealing with? The x direction or the y direction?
The X. The X.
If I deal with the x direction, I get normal force minus normal force equals 0. I get normal force equals normal force. That's not going to do me any good. Yeah, I want y direction. Also because I know the weight. The weight is 9.8 newtons. So if I define up as positive and to the right as positive, then I got some of the forces in the y direction equals MAY. I got two of these static friction forces acting up. I got my weight acting down. That's equal to 0. So I got 2 times mu sub s f sub n equals 9.8 newtons, or 2 times mu sub 2 times 0.60 times normal force equals 9.8 newtons. And so I get my normal force equaling approximately 8.2 newtons. You're going to end up with 2 problems like this between tonight and tomorrow night's homework. One problem where you're pressing a book against the wall, and another problem where someone is pressing a book between their 2 hands. But they're both done the same way. You end up having 2 normal forces, 2 friction forces, and the weight. So I'm showing you these problems to show you techniques. Like, the big thing I want you to get from the lawnmower is make sure that your components have arrows on them, because that'll affect normal force. The thing I want you to get from this is just this interplay between normal force and friction force. The last thing I need to show you is the helicopter problem. And that one is dealing with x and y components of unknown forces. So, and then we'll be done. Here. Does that look sufficiently like a helicopter?
Yes.
Good, good. I'm very proud of that helicopter. I think it's unmistakably a helicopter. There happens to be 3 forces acting on this helicopter. You've got the weight of the helicopter, which is known to be 55,000 newtons. You've got the lift of the blades, which is acting at a 30-degree angle to the vertical. And then the third force on this helicopter is air resistance, because it's moving horizontally at a constant velocity. This is the picture they give you in the textbook. And they want you to get the lift and the air resistance. What's the big lesson I want you to get from this? I will tell you. Ordinarily, when I have a force at a weird angle, what do I find? X and Y components, absolutely. But what happens if I don't know what the force is, right? Then what am I going to call the X and Y components? Well, just call them L sub X and L sub Y. Just the lift, we don't know what the lift is, but it starts with the letter L. So I'm going to call that L sub X and I'll call that L sub Y. And that's the strategy I want to give you. You don't have to give up just because you don't know what the force is, so you can't find the X and Y components. Go ahead and give the X and Y components names, and then you can find the X and Y components. Which direction would you like me to do first? Some of the forces in the X direction or some of the forces in the Y direction?
Why?
Why, Justin, why the Y?
Because we know the mg.
Yeah, because we know the weight. I know I got information in the Y direction. I don't have any information in the X direction. So let's go ahead and go with the Y direction. I'll define up as positive and to the right as positive. So I got some of the forces in the Y direction equals MAY. I got the Y component of lift minus the 55,000 Newton weight is equal to 0. 0 because it's traveling at a constant velocity, so there's no acceleration. So I got the Y component of lift. Yay. Now that I know what the y component of lift is, can I find what the lift itself is? Yeah, you use trigonometry. You're going to say that the cosine of 30 degrees equals the y component of lift over the lift itself. And so the lift is going to equal the y component of the lift divided by the cosine of 30 degrees. And that ends up being, I think it's like 63,500 newtons. Hi. Thank you. 1220, get out of jail free. This will probably be done in like a minute. So you guys okay that I answered the first problem? I got the lift. It's 63,000. Now it's time for me to get the air resistance. And I'll just do some of the forces in the x direction, equals max. So I got the x component of lift minus the air resistance, and again it equals 0 because there's no acceleration in the x direction. Because yes?
If you found it in the y direction, why did you use cosine of 30 rather than sine?
Because I'm looking at my triangle, and this is the adjacent leg, and that's the hypotenuse, so I went with cosine because it's adjacent of hypotenuse. What the big fake out here, though, Chris, is they gave me the angle relative to the vertical. When they give you the angle relative to the vertical rather than the horizontal like we normally have, then it turns out the y is cosine and the x is sine. Well, yeah. So me personally, I may have even decided to say this is 60, and then I get back my x being cosine and my y being sine if I make it a 60-degree angle. That's weird. Alrighty, so L sub x is going to be lift times the sine of 30 degrees, and that's going to equal my r, and so I got 63,500 times the sine of 30 degrees equals my air resistance. So that's going to be what, 31,800, something like that. Alrighty, so you're going to get a problem like this, and I just want you to see it's not a scary problem as long as for the unknown force you label the x and y components as L sub x and L sub y, and then you end up just being able to find them separately. And we're done. Turn that thing off before I say something.